In this video, we will go over electromagnetic radiation. Before we do that, a couple of main points. Number one, you always have to think of an electron, which is really the brunt of this section on this chapter. An electron is both a wave and a particle. So this idea or this recurrent theme is wave-particle duality. That is with regard to the electron, which is the subatomic particle that orbits the nucleus. Remember, the nucleus containing protons and neutrons. So recognizing that an electron can behave as both a wave and both as a particle, we're going to decipher now this term or this concept of electromagnetic energy. Now we're looking at electrons in terms of their wave-like behavior. So now let's discuss the anatomy of a wave. So waves oscillate and there are propagations. Waves also contain within them certain packets of energy. We call that packet of energy a quanta. Now if you compare and contrast the anatomy of a wave, if you go from the highest point of the wave to the next highest point of the wave, that is to say amplitude to amplitude, or the lowest point of the wave to the next lowest point of the wave, or going to this point here, node, where it has zero energy, to the next node. So from like point to another like point in the wave, we call that a wavelength. And that wavelength is a distance, and it's usually expressed in terms of nanometers. A nanometer is 10 to the minus 9 meters. Now remember, these waves propagate. So the speed at which a wave propagates, or any type of velocity that the wave goes, is called the frequency. And the units of frequency is the hertz, 1/seconds. To better understand frequency, imagine that there's a human being standing right here, right on the edge here. Now looking at wave 1 versus wave 2, you'll realize that as these waves propagate, this wave will pass through the human being here at a much slower rate than the person who's standing here. This person standing in this below wave will actually have the wave pass by through him or her many, many, many times. That is to say, the wave will hit this person. The frequency at which the wave hits this person is much higher. So frequency is just a fancy word for speed. Now, if you look at the relationship between wavelength and frequency, you'll find that as the wavelength increases, the frequency, the speed of the wave decreases. We have what's called an inverse indirect proportion. As wavelength goes up, the speed goes down, or the frequency is the more apt term. Now look at this in contrasting to this bottom wave. Look at the wavelength here. The wavelength is pretty small, okay? But what can we say about the frequency? Okay, we can say the frequency is very fast. So the wavelength and frequency have a sort of an indirect relationship. As one goes up, the other one goes down. Another important point to recognize is they have energy. There's energy contained within waves. You probably feel that when you have sun waves or UV waves, hit you. Okay? There's sort of energy that hits your face, and you begin to realize this. So waves have energy. An electron can be considered a wave, but it can also be considered a particle. Okay, that's the conundrum in quantum mechanics. And another thing we want to talk about is this idea of electromagnetic radiation, which is really the theme of this lecture. In electromagnetic radiation, the wavelength and frequency equal the speed of light. And the speed of light is a constant, 3 times 10 to the 8 meters per second. The electromagnetic radiation are just waves, special type of waves. It is two waves that travel perpendicularly to each other. So electromagnetic radiation consists of electromagnetic waves, and in the previous slide we talked about wavelength and frequency. Remember, as one goes up, one goes down, the other goes down. But they're two waves traveling mutually perpendicular to each other. You have a magnetic field wave traveling perpendicularly to an electric field wave. So that's all you need to know with regards to electromagnetic radiation. The electromagnetic spectrum, which consists of all these different types of radiation, is just this. It's just an electromagnetic wave, but which consists of an electric field traveling perpendicularly to a magnetic field. Those two waves are traveling perpendicularly to each other. A lot of students get this wrong when they think of electromagnetic radiation. They fail to realize that it's actually two waves traveling mutually perpendicularly at 90 degrees to each other. Once again, it is an electric field wave and a magnetic field wave. This was proposed by Maxwell. And another thing that it's very important to realize is that this radiation travels at the speed of light. That speed of light is 3 times 10 to the 8 meters per second. It's a constant that I will give you on the exam or any type of examination. However, it may be good to memorize that. So an important relationship here is the wavelength of a wave times the frequency of the wave. Frequency here is V, and that equals the speed of light, whose abbreviation is C. This wavelength here, which is a length, is designated by the Greek letter lambda. Within that spectrum, you have gamma rays at one end. We're going to call this the high energy region of the electromagnetic spectrum. Okay, notice the wavelength is very small, but the frequency 10 to the 20 is very high. And it spans all the way to the lower energy. The lower energy, kind of harmless to us, such as radio. This has a very long wavelength, 10 to the 13, okay, extraordinarily massive length in nanometers. The frequency is very, very small, 10 to the 4th. So on one end here, you have low energy, things that really are not harmful. And then here at the other end, we have high energy, things that can get potentially harmful, such as gamma rays, even X-rays, which are very powerful. They're so powerful that they can penetrate tissues. That's why when you have X-rays, it's usually done at a low dose, and they cover you up with, shields and stuff like that. And then you have all this other electromagnetic radiation in between. You have UV waves, you have infrared, microwave. You have a slither here that we can actually see. Okay, so that's the visible region of the electromagnetic spectrum. The visible region of the electromagnetic spectrum are the colors. There's 7 principal colors, and it's Roy G. Biv: red, orange, yellow, green, blue, indigo, and violet. So here you have sort of the low energy end, and here you have the high energy end. So we have regions of the electromagnetic spectrum that we can see. We have regions that we can hear, and then we have regions that are high enough energy that are dangerous to us. However, we can also clinically use them, as in the case of X-rays. We also have regions of the electromagnetic spectrum that we utilize, such as UV, microwave. All of these travel at the speed of light. All of these are magnetic field waves traveling perpendicularly to electric field waves. That is the electromagnetic spectrum. That is the electromagnetic wave. It's electric field wave traveling perpendicularly to the magnetic field wave. That's a very important point. The second important point is that they travel at the speed of light. Another thing that we want to talk about here is emissions. So if you heat an object like a metal, it will actually emit. It will emit, and it will emit electromagnetic radiation. You have to get the right quanta. You have to get the right energy. That is what really a quanta is. It's just a discrete packet of energy. If you get the right quanta of energy, what happens is that you kick out an electron to a higher energy state. When you kick out an electron to the higher energy state, it is excitation. Now, we're not ejecting the electron out of the atom. Okay, please be aware, we're not kicking out the electron from the whole atom and liberating it. We're just taking the electron with the right amount of energy, nothing more, nothing less. It's not like you put so much energy and then the electron moves. It's just the right amount of energy, henceforth the term quanta. You can energize an electron, excite the electron from, let's say, energy level 1 to energy level 2, all of this within the atom. So after excitation, what happens is that, like any child or like anything that's wound up, it relaxes. So when an electron relaxes, we call that emission. And that emission is in the electromagnetic spectrum. It could be UV emission, it could be visible emission, that is, we can see it. It could be IR, infrared emission. So there is excitation and emission, and all elements of the periodic table have an emission spectrum. So having said that, we come across another equation that is the energy. So that energy contained within this radiation is Planck's constant times the frequency, realizing that the frequency times wavelength lambda is equal to the speed of light as well. So this is the photoelectric effect that was enumerated by Einstein around the 1900s or so. The main point here is light is both wave and particle. I mentioned that an electron is both wave and particle, but light also contains this dual nature. But I want to tell you that light is nothing more than packets of electrons. That is to say, photons of electrons. So here we have this new fancy term called a photon. It's just thinking of these electrons as more particle. Even though they're wave and particle, we're going to use photon as more of as the term that designates this batch of electrons in their particle form. So what Einstein basically mentioned is that if you excite a piece of matter, in this case a metal, electrons get excited to a higher energy level. That's excitation. They relax back to the ground state, that is relaxation. When they relax, they emit, that is emission, but they will emit, according to Einstein, not just electromagnetic radiation, but they will emit it in the form of photons. So photons is just a way of describing this electrons in terms of its particle nature.